All right, so to continue with chapter 18, the second part of the chapter talks about a device that we call capacitor. So these devices, the capacitors, are specifically designed to have two conductors in the configuration. So you can see conductor A, conductor B, and these two conductors always have the same charge, plus Q, minus Q. One is positive, the other one is negative. And technically, this capacitor as a device comes in different size and shapes, as you can see in the image on the left. So the idea here is it can be there's two plates, which we're going to be considering actually. Could be two cylinders, could be two spheres and things like that, right? So in a way, in the industry, those are the type of, let's say, capacitors we use. So you can see, right, this one is kind of like cylindrical, this is a little bit different, right? But the idea here is always two, let's say two conductors. One always going to be charged as positive, the other one is charged as negative. And they're mostly used such that as soon as you have electric field, you can see right between those conductors, those electric fields then can be used to store energy, because electric energy, electric potential energy is stored in those electric field lines. All right, so in photography, if you ever use those flash photography, especially like the old ones of like Kodak, let's say the cameras, those photographers would always have a flash that required, actually there was a little wheel where you have to rotate in order to charge the capacitor, and you take a picture and then you had to rotate that again. Because one of the things you do over there is when you're rotating, you're doing mechanical work, which, mechanical work transfers mechanical energy, which then converted into electric energy, then stored in a flash. And then when you take a picture, that energy in the capacitor is used for basically to create a light, right? So you can see, right, that there's a light bulb that works because of that. And then once you used up all that energy, you would end up, rotating it again, charging it again, sort of like, let's say, to use it. So in a way, the capacitors are devices that you can store energy, but for a temporary use. You don't really have a way of storing energy and using and reusing all over again. So that's why, they're useful, because you can store some energy over there, but that energy here is, cannot stay there for, forever. So for example, battery, AA, AAA, they can store energy, and then you can use them use that battery for a very long time. Well, that's because battery has chemicals inside, and those chemicals are, generating chemical energy when they, let's say, react with one another, and that reaction generates chemical energy, which is then converted to electrical energy eventually, and then you can, power your I don't know, remote controls and so on and so forth. But they have, those batteries have a lot of chemicals, so they can use that process all over again for a very long time, maybe let's say months or years, depending on what you're using it for. Capacitors don't have that ability. You can store charges, but once you use it, those charges can dissipate within minutes pretty much, or seconds, for example. In any case, so let's kind of, have a basic idea of capacitor, which is again two conductors, A and B, and they're connected such that then they shouldn't, let's say they don't have to, let's say be physically connected. There's always a gap between capacitor conductors, but they are separated with some kind of like, let's say, distance D. So there's a distance D that separates them. Most of the time, that distance between them is either vacuum or maybe like, let's say, some kind of material that you can put. We're going to talk about that later on. We call them, so those insulators, right? So we call them dielectrics. So, but in any case, so let's say you have two conductors. And one of the things we're going to see is they're always going to be charged with the same magnitude. Okay, so when they charge with the same magnitude, that that magnitude basically always the same. One is positive, one is negative. And let me tell you, let's say, why that's the case. For example, we take those conductors, and let's say that this conductor A, this is conductor B. Initially, they're neutral. That means you have same amount of, let's say, positive and negative charges, right? Then what we do here is we use some kind of power supply. So again, power supply is just like a battery. It has two terminals, positive, negative. And these terminals basically has a, they have a potential difference between them. So let's say V, let me put like, delta V, right? Delta V here is, the difference between positive and negative, V plus minus V minus. So let's say delta V here is 10 volts. So what we do generally, we take positive then to be 10 volts, and we take the negative to be 0 volts. That's the, general, let's say idea. Even those AA, AAA batteries, the one that says negative is 0 volts. The one that is positive, 1.5. So their voltage is the potential difference. Their voltage is 1.5 because their potential difference 1.5. All right, so let's say we do this. And we take then the positive plate, positive terminal, and connect it to conductor A, and then negative connected to conductor B. So what happens then when we do that? Well, what happens here is that, this becomes sort of like a circuit where there is an electric field. There is an electric field that then will start from positive plate, and it will go toward the, let's say, conductor A. So that's the electric field. So this is, let's say, the electric field. And then the electric field will go from A to B, right? Just like you can see, right? So basically, and then come back like this. All right. Now, that means there's an electric field everywhere in your circuit like that, starting from plus, going around, coming back to minus. Okay. Now, remember one of the things we have here is this. This particular conductor, if it's, let's say, neutral, means it has equal amount of positive and negative stuff. So let's say it has equal amount of positive and negative stuff. So let's say 1, 2, 3, 4. 1, 2, 3, 4. But then there is electric field. And what electric field does, it affects the charges in those conductors. Well, when those charges are affected by this conductor, then what happens here is they start moving because there's electric field, and electric field exerts force. If you remember chapter 17, we talked about that generally the charges that are moving from, from a conductor or one conductor to another are always the negative charges. That means what we're going to happen here is this. This negative charge going to be moved from this conductor to the other conductor. That means this guy then gets an extra negative. Then the second negative, all right, not what I wanted to do. Okay, so then the second negative goes from, let's say here, right, goes all the way to the other side. Okay, the idea is that then, let's say if you start moving the negatives from plate conductor A to conductor B, then eventually what you're going to get here is this. Wow. So let's say eventually what we're going to get here is conductor A right, so I'll just start over in terms of that. So conductor A now going to have, let's say, some of its negative moved, which means that now it has more positive because some of its negative moved. And then conductor B now going to have more negatives. And the same amount of positive and negatives are the same because what are we doing? So for example, right, we took 4 negatives and we moved it from there to here. That means A has 4 less negatives, B has 4 more negatives. So this becomes positively charged, this becomes negatively charged. And the Q is the same because all we're doing, you're taking some amount from A, moving to B. That means how much, more plus the A has is exactly the same amount more negative B has, right? Because we just moved the same amount from one to the other. So that's why Qs are always the same for the capacitor. And that makes sure that, let's say, it doesn't matter, let's say if you have any type of conductors, let's say plates, or let's say two let's say, cylinders or two spheres, right? You always get basically the same. You are moving from one to another. So these plus and minuses for A and B right now represent that extra it has. So A has extra 4, B has extra, extra 4 positive, B has extra 4 negative, right? So then we can say then the Q is the same. You just in one case it's extra positive, the other one is extra negative. All right. So hopefully it's clear why they always have the same amount of charge. Okay. Then what we can say with, when the capacitor is charged, it means that two conductors have charges with equal magnitude and opposite sign, and the net charge on the capacitor as a whole is 0. Because remember, it was initially neutral, same amount. And now this, even though this is plus Q, this is minus Q, these Q's represent extra charge. So if you add them together, let's say Q plus Q minus, you should get 0 because the net here is 0. All you did just move one from another, conservation of charge, if you remember. All right, so then one, let's say configuration that we're going to be considering is known as parallel plate. Okay, so parallel plate takes two, plates, which we kind of already seen before. So it takes two plates and charges them, positive and negative. So, but one of the things we have here is this. So let's say, even for that one, right? So let's say we had, A, we had B, and this was the battery, plus, minus. So we connect it like this, if you remember. Okay. So now, remember, this VAB is the battery voltage. VAB is the battery voltage. Usually what we call potential difference VAB. Okay. But because positive terminal connected to A, it makes A positively charged. Negative terminal connected to B makes it negatively charged because charges, right, move from positive to negative. Also, what we get here is since, conductor A is connected to positive terminal, it has exactly same potential as a positive terminal, which was in previous example slide, right? This was 10 volts. Conductor B gets the same potential as the negative terminal because it's electrically connected to that, which means, so in this case, let's say VA is 10 volts, then VB here is 0 volts. Then you can say, right, potential difference VAB between the conductors is equal to the voltage of the battery, because conductor A electrically connected to positive plate, and positive plate has 10 volts. Conductor B to the negative plate, and negative plate was 0 volts. So that means conductors now have exactly same potential as the battery. Then if we change the magnitude of the charge on each conductor, the potential difference between conductors changes. Okay, that means if I move more, Q's from A to B, then technically the potential between them will change. But I can only do that if I'm technically changing the potential here as well. Okay, because one of the things I have here is this. See this, how much Q I have over there depends on electric field that I have in the system, right? That because electric field is what, pushes those charges. But remember that electric field also depends on voltage, right? So electric field is equals to V over D. That means how much electric field I have depends on how much voltage I have, which means they're all related. So that means if I take the ratio of Q in the system, and I can use just one Q because the QA, QB are the same, so just Q, the amount of charge, and divided by the V of the capacitor, that means potential difference between, because this is my capacitor, right? Potential difference between capacitor, those conductors, is Q over VC. This ratio will always be constant. Because if I take my battery voltage, let's say V battery, and let's say make this 20 volts instead of 10 volts, that means this becomes 20 volts. This becomes 0 volts. And that means more charges will go, from A to B in this direction. It means that thing like this, if I doubling the voltage, I'm doubling the charges that will go from A to B. If I make this 10 times, this will be 10 times. That means that the ratio is always going to be the same, and that the ratio is defined as the capacitance of the capacitor. You can see, right? The ratio of the charge potential difference does not change. So that means this ratio is called the capacitance C of the capacitor, and we're given with this equation. That means take the Q, which is the magnitude of the charge on each conductor, divided by VAB, which is potential difference between the conductors. Usually I write as VC, voltage of the capacitor, right? Then that ratio is known as the capacitance of the capacitor. So sort of like how much it can store, right? It's storage space, okay? And the units are, you can see, right? If I do Q versus V, Q over C, sorry, Q over VC, this is then coulomb per volts, But then we take that unit and we define then coulomb per volt as a unit. We define that to be farad, F or farad like this. That's actually after Michael Faraday, because Michael Faraday did a lot of discoveries in electricity and magnetism, and the units is basically, after him. That means any type of conductor, regardless of its size or shape, can be, applied this equation on. That means if I know the conductor charge, if I know the voltage between conductors, that means the voltage of my capacitor as a system, then charge over the voltage, right? This equation will give me the capacitance. So for example, in capacitance, it's a number that represents, it's sort of like how much storage it has. So for example, you have 20 and let's say maybe like microfarad. And then if I compare it to another one, which is let's say 100 microfarad, well, that means this one can store 5 times more than this guy. That means greater the value of the capacitance, more charges it can store, more potential difference will be between the plates and things like that. That means capacitance is a number that generally going to be small. Don't expect the capacitance to be in hundreds or thousands or things like that. Let me give you sort of like a range. So generally it's going to be from, let's say, picofarad. Pico is 10 to the negative 12 farad to roughly microfarad. And micro here is 10 to the negative 6 farad. That means this is sort of like the range for the capacitors. They're very small. That means it's in pico and nano and micro, maybe milli, that's highest you can go. But generally it's micro and nano. That's kind of like what we're going to be seeing. All right. So for example, then this is a parallel plate, which we have seen before, remember? So here's a positive plate, here's a negative plate, right? And then we said there's electric field between them, uniform and things like that. Well, technically we were talking about capacitor, we just didn't know at the time. So let's say you take those two plates, you take some kind of, like battery or a power source with a positive terminal and negative terminal. So take this and connect to the, using a wire, right, to the top plate. Well, since the top plate connected to positive terminal, it has plus Q, because remember, what we do here, we take the negative charges and move from here to there. So let's say if this guy here is the negative connected to here, right? We move the negative charges from here to there. So this becomes positively charged, the other one becomes negatively charged. That means what we get here is this also. Voltage of plus, voltage of minus terminals. That means I can say that plate A has the same voltage as the positive terminal, and then the voltage of B is the same voltage as the negative terminal, which generally means it's 0. So then delta V is, in this case, if I have just this capacitor, one capacitor connected to the battery, that means its potential difference is equals to the voltage of the battery. It means voltage of the capacitor, put VC, that means voltage, which means kind of potential difference. So VC, that means voltage of the capacitor, is same as voltage of the battery. Again, hopefully you guys remember, right? When I'm talking about voltage, I'm talking about potential difference between 2 points. So instead of saying potential, I'm saying voltage, which implies that it's a potential difference between 2 points. All right. Now, what do we have about the parallel plate? So parallel plate is a specific configuration, 2 plates of equal area. Plate A has area A, plate B has area A. That means same area. And they are separated by distance D. Okay, so you can think of like this is basically, exactly that, right? 2 plates separated by distance D. Here's area for both of them exactly the same. Okay. Now you can see, right, potential difference equals VAB, which is what we call voltage. So if I connect, right, let's say if I connect, remember, there is then an electric field, right? There's an electric field going like this and like that. That means in this case, for example, clockwise direction, and also between the plates. So there's an electric field sort of like between the plates. And this electric field, right, lives between the plates, okay? And what it does here is then it's responsible for charging it. Now, as it's going to start charging, initially, let's say at t equals 0, Q is equals to 0, because remember at t equals 0, as soon as I connect the battery to the plates are neutral, so that there was no charges. And remember, Q represents extra charges it has, right? But then as a function of time, then I start increasing Q, right? I start increasing Q. And as the Q between the plates starts increasing, so is the VC, right? Starts increasing. So VC starts increasing as Q starts increasing. Because at t equals 0, Q is 0, and also at t equals 0, V of the capacitor equals 0. See, V of the battery is not 0 to start with, but the voltage of the capacitor is 0, because when they're neutral, there's no potential difference between those two plates. So these are our initial conditions. At t equals 0, there are no charges on the plates, and they don't have potential difference. But as a function of time, right, maybe it takes 5 seconds, 10 seconds, microseconds maybe, these charges start moving, and then the potential difference here starts increasing. So when it's going to stop? Well, it's going to stop when the voltage of the capacitor matches the voltage of the battery. So when they match the voltage of the battery, that means you can say it's fully charged. Okay, so when it's fully charged, whatever the time is, then the electric field basically goes to 0. That means there's no more electric field, nothing is pushing. And then as nothing pushes, right, then what we get here is, charges basically stop moving. That means we can say that our capacitor is fully charged. That means capacitor is fully charged when the capacitor potential difference, right, capacitor voltage matches the battery voltage. Okay. So in this case, then one thing we can do here is this. So the field between the plates of parallel plate capacitor is essentially uniform, those electric fields between the plates. And the charges on the plates are uniformly distributed over their opposing surfaces. When the region between the plates is empty, the capacitor is, that means, the area or like the space between the capacitor is empty, so it's vacuum. So I can still apply this equation. I can say, all right, so if I know the amount of charge on the capacitor plates and then voltage of the capacitance, that ratio gives me how much capacitance I have. But if it is a parallel plate capacitor with vacuum between the plates, then there's another equation that I can also use. And this is where it says the capacitance is proportional to the area of the plates. That means bigger the plates, more charges I can store. That means A area would increase the capacitance. But it's also inversely proportional to distance. That means actually if I move the capacitor plates from one another, capacitance would decrease. And I go from proportionality sign to equal sign. I introduce a constant, and that's the constant electric constant. Remember that epsilon naught that I talked about? So this epsilon naught A over D. That means this is another equation for the capacitance, but more specifically to parallel plates, basically. That means this equation is used for any capacitor, including parallel plates. But this one here is only specifically for parallel plates, because this takes into account configuration or the geometry of the parallel plate, because it has area, it has distance, and things like that. So you can see, right, capacitance increase if area increases, but capacitor decrease if distance are increasing. That means distance increase gives you, smaller capacitance. All right, so let me clean this up. Okay, so the capacitance depends on only the geometry of the capacitor. Because remember, as I mentioned, right, if I try to, let's say, because it's connected to those plates, right? So let me do it like this. So let's say I'm going to put them like this, kind of like, two-dimensional. So if I increase my voltage, see if I increase my voltage, I'm increasing the Q. And then Q over V is still going to give me the same capacitance. That's why by changing the amount of voltage in the battery and things like that, I'm not going to be changing capacitance, because capacitance is just basically how much this guy can store regardless, what I have. Think like a room, right? So let's say if you have a room, this room can store a certain amount of people. Doesn't matter if you have 10 people there or 100 people. Let's say if it stores 200 people maximum, right? So you can have different amount of people over there. So you can have a bigger door, have more more people going, or smaller door has less people going at, in terms of rate. But what you have here is it has 200 people, let's say, maximum capacitance, right? How many people you have over there? It doesn't matter. In a way, like let's say that number depends on the geometry. That means the shape of the room, width, height, and length, right? Same thing is the capacitance. So then the quantities A and D are constants for a given capacitor. And this epsilon naught is a universal constant. Remember, this epsilon naught is 8.85 times 10 to the negative 12. Coulomb square over Newton meter square. So that's the number for the, for epsilon naught. All right, so let me show you something. Okay, so here's an example of a capacitor. So let's say we have a battery on the left side and you have two plates. And for now, you can see that as long as I have here, as you can see, right, this is 0 voltage, there is nothing, right? So the capacitors are neutral or not charged. So then what I can do here is this, just move this and start charging. See, as soon as let's say I go here, I am not using the entire, let's say, 1.5 volts. I'm using maybe like 1 volt. So let's see if we have a way of, so we're going to use meters. So give me capacitance, sitting like this. If I move this here, see right now, reset all. For example, I want electric fields, capacitance, plate, stored energy, and voltmeter. So we're going to have these guys over here. So then what I have is this. See the capacitance right now given as, so this bar here, right? Given as 0.89 times 10 to the negative 13 farad. And see, it's not 0. Why? Because, I have two plates, right? And capacitance is equals to epsilon naught A over D, right? Epsilon naught A over D. That means right now, I have a capacitance. That means, just amount of storage it has. What I have here is then this. So let's say I can charge it by increasing the voltage. See, let's say if I go and you can see, right? So how much voltage do I have? Well, one thing I can do, I can use this voltmeter, go here, and the other one here. Okay. There you go. So you have the voltage, 0.625. Then what I have here is you can see, right? Now the capacitor is charged. Capacitor is charged. There are positive plates and negative plates, and there's electric field, right? So then there's electric field, and then I can see that plate charge at the top is 0.55 times 10 to the negative 13. Stored energy, 0.17 times 10 to the negative 13 joules. All right, so what I have here is then I can make this, let's say, see, look at the capacitor is still the same. If I increase the voltage to 1.5, for example, plate charge is at maximum, because let's say I can't increase the voltage anymore. So voltmeter shows me 1.5. Then you can see, right? Look at the electric field between the plates. It increases, becomes, remember, closer they are, stronger the magnitude. And look at, as I'm changing this, really, the electrons are moving, right? And they move from one plate to another, and then I have it fully charged. Capacitance value is still the same. Now let's try to measure the voltage between the plates. So from here to there. See, it's 1.5. I tried somewhere in the middle, see, I need some kind of conductor to conductor. See, 1.5. That means Capacitor has the same voltage as the battery. Now, see, the capacitance didn't change. See, as I change the voltage, I'm changing the amount of charge, but I'm not changing the capacitance. How do I change the capacitance? Well, using, I can change it only if I change those quantities right now. That means if I change the area, for example, see, I'm changing the area, look at the capacitance, see how it increases, right? It increases. That means I can now store more energy, more charges. See, I have more charges compared to before, see? I have more charges compared to before. Well, how else can I change the capacitance? Well, I can change by changing the distance between, see? Increased distance decreases capacitance. Decreased distance increases capacitance. By the way, I'm going to post something like this on Canvas so you guys can play with that. All right, so I think I might actually have it right now, so check it out. So then what I can do here is this, right? So I can still have still saying 1.5 volts, but capacitance changes because I'm changing the geometry of the capacitor itself. All right, so let's go back to the lecture. Okay, so that means, the units of capacitor is farad, you can see, right? So this is Coulomb per volts, because Q over V, right? Coulomb per volts, or Coulomb square per newtons times meters. They're basically different ways of kind of putting together. But, this is basically, remember that, farad is the units of the capacitance. Is a, 1 farad is a very large capacitance. That's why we have roughly a millionth of a farad is just a kind of like, let's say, the norm. So that's for the commercial use, right? So you can see, right, this looks nothing like a parallel plate or something like that. But, this is a cylindrical capacitor. So most of the, capacitors look nothing like a parallel plate. But, there are parallel plates are just easier to work with. All right, so we're going to start drawing a circuit diagrams. That means, every time there is a capacitor in a circuit, instead of doing the, like pictures and things like that, we're going to do diagrams. This is some capacitor symbol. That means every time there's a capacitor, I can represent it like this. So the capacitor, 2 plates. Those are just wires connected to other things. So, and what we always use, like a straight line to represent the wires that we use to connect. So you can see, right, the circuit diagram is a simplified representation of an actual circuit. Circuit symbols are used to represent the various elements. Lines are used to represent wires. The battery's positive terminal is at the higher potential and is indicated by the longer line. So you can see right here's the battery, a longer line for the positive, shorter line for the negative. So we usually put positive and negative. We can also use a switch, just like the light switch, right? So open means that, let's say, there is no path. So that means there's an open, right? There's no electricity going. When we close, it's like turning on the switch. So now there's electric field, you can think like that. So there's no electric field here because there's a gap, but there's electric field now, which moves the charges and things like that. That means if I go back and look at, for example, this particular picture that we did, right? So let me kind of clean everything. So over here, what I can do is this. See, this is a plate. I can represent it like this. This is a capacitor. So these are the lines, which are the wires. And then let's say here I have a battery. So I can represent it like this: positive terminal, negative terminal, longer and shorter. Then this is line, a wire connecting the battery to the capacitor, the negative terminal to the other side. So this is positive terminal, this is negative terminal. I would usually put VB for the voltage of the battery. And then as soon as I make this connection, I have then a charging of a capacitor, which is going to make this one is positive, this one is negative. Okay, then I can represent this Q. I don't need to put plus Q minus Q, but you can do that if you want to. And then what I have here is the potential difference here is VC for the battery, for the capacitor. All right, so that means we're going to be start using this. We're going to be start using the symbols. And then what I have here is this. So basically then when I have, for example, here's a capacitor and here's my battery. So, and sometimes I can do the switch like this. And here's a wire connected to the capacitor and like this. So this C is for my capacitor, VB is for my battery. Positive terminal, negative terminal. Then think like this. So if I have, for example, right, if I have 10 volts, and if I have, for example, if I close the switch in order for the charges to go, that's how I represent it, like an arrow but down. Then let's say here's my Q, plus Q minus Q. So plus plus minus minus. So let's say my Q happened to be then 10 times 10 to the negative 9 Coulomb. Then how much is the capacitance? Well, C here is equals to Q over V. So 10 times 10 to the negative 9 over 10 volts. Then what I get here is basically 1 times 10 to the negative 9 farad. That means that's my capacitance. Okay, just when you have just one capacitor, just as simple as that. You know, Q divided by that. Is there another way I can find the capacitance? Yes, remember, I can find the capacitance, you know, by taking the epsilon naught, if I know the area of the capacitive plates and the distance between the plates. Same thing, you know, going to be calculated with this equation. Things become more interesting when you have more than one capacitor, actually. So we're going to look at capacitors, you know, basically multiple capacitors in your circuit. So you can have 2, 3, 4, 5, 6, and so on and so forth. And it actually gives you a lot of options. Interesting enough, when you put more than one capacitor in your circuit, so they're kind of like the obvious, you know, the thinking would be like, okay, so if you put, you know, several capacitors together, you usually would be then increasing the capacitance. And it is true. You can increase the capacitance if you put more than one capacitor. Surprisingly enough, you can also decrease the capacitance. That means you put 2, 3 together in some configuration and you have less capacitance, less storage than before. How is it even possible, right? But it is. With the capacitors, you can do that. You can put capacitors such way that you're actually decreasing your sort of like storage. All right, so in a way, you can think of like it's also possible with the room, right? See, if you have a room like this, see if I put another room like this next to that, I can fit more people, right? So now, right now I can fit twice the amount of people. But if I take this, and then let's say this is my first room, and I put the second room right on top, right? But not really giving the people, like, let's say, option to go up or something like that, right? So basically, I'm not doing anything, right? I'm not doing myself any favor by putting another room right above, because people can only be on the first floor, let's say, but they can never go above or something like that, right? So here's just showing that, you know, you can put two things together, but not really have any advantage of that. For the capacitors, actually, by putting two things together, you can even decrease the capacitance, which probably was not the case in my, you know, second picture over there. All right, so then let's see what we get. There are two configurations that we're going to be considering. Capacitors in, so series and parallel. And here's what I have. One of those increase the capacitance when I put multiple together. The other one decreases the capacitance if I put multiple together. So let's see which one is what. And there are a lot of things going on when you have, you know, more than one capacitor. And I highly recommend you guys use those simulations to kind of play with that to figure out, let's say, what's going on. So for example, then what I have here is this. So this AB are 2 points of the battery. So let's say here's the battery like this. Okay, positive terminal, negative terminal. But now I have two capacitors. Okay, that means I have one capacitor, C1, and it's connected to the second one, which is C2. Okay. All right, so here's then what we get. If you have two capacitors in series, and we're going to look at that, so capacitors in series, if they're connected to one another, as illustrated in the picture before. That means what you have here is that you have the first one, C1, you put the second one, C2, and you connect them only at one end. That means, you know, they're connected by one wire. Okay. The second wire connected to C1 and the second wire connected to C2, they're not connected to each other. That means they're not connected to the capacitor. So let's say you take a battery here, positive, negative terminals, and let's say C1, the other wire connected to the battery, and C2, the other wire, let's say, for example, connected to the negative terminal. That means only through this wire, right, those two are connected. Okay, now let's see what happens. When I take this VB, which is battery voltage, and let's say there was a switch and I close the switch, right, and now remember what happens? Electric field. Electric field goes like this, goes like that, goes like this, goes like that, goes like this, and then comes back to the negative plate. One of the things we can see here is the electric field the entire time has only one path, right? One path, which means it doesn't jump, let's say branch away or something like that. And if this is the case, that means both capacitor 1 and capacitor 2, they have the same magnitude of the electric field the entire time, right? Same electric field acting on C1 and C2. That means how much charge will go from C1, or let's say how much it will be charged, is exactly the same by how much the capacitor 2 will be charged, okay? And technically what it does, it takes the charge from here and moves it to here. And then take one from here to move it there. Okay, so that's kind of, from here to there, so that's kind of what it does. But let's say the idea here is this. There are two conditions that must be satisfied, assuming that you're dealing with a series configuration. Because electric field has only one path, C1 and C2 have the same electric field, same magnitude, right? That means Q1 is the same as Q2, always. Q1 is same as Q2. That means how much C1 is charged, same C2 is charged. That means I can just say Q, which is the, let's say Q series, right? And they're the same. That means any two capacitors, any three capacitors, any 100 capacitors, if they're connected in series, they're all gonna have the same, amount of charge, let's say when they're charged, right? So the Q is gonna be the same for capacitors in series. All right, so about the second condition. Well, the second condition has something to do with voltage. Because for example, if I have a voltage from the battery that my battery provides, and let's say this is 10 volts. That means battery provides the total voltage to the system. That means battery is what provides power to my circuit. And it's 10 volts. That means, that's the maximum amount I can have as a voltage. Now think like this. If I take this 10 volt and I give it to the C1, then there will be nothing for C2. All right, that means, you cannot give everything to C1. There has to be something left for C2. Well, how much C1 gets and how much C2 gets, well, depends on a number of things, and mainly that, depends on the value of C1 and C2. For example, if C1 and C2 are the same, then exactly half of this 10 is given to C1, and the other half given to C2. That means they get equal share of the 10 volts. All right, that means what I have here is the V battery is equals to V1, voltage across capacitor 1, plus V2, voltage across capacitor 2. Okay, so if C1, let's say here in this case, C1 equals C2, so each get the same share of voltage. And if you take the algebraic sum of voltage 1 and voltage 2, voltage of capacitor 1 plus voltage of capacitor 2, you will get the total voltage, right? 5 volts plus 5 volts, you get VB, which is 10 volts. Because the total, right, it should be equivalent to the battery voltage, regardless. Okay. Now, that means one of the things we have here is, you can see, right, the voltage is distributed to your capacitors in series. That means 2 capacitors, 3 capacitors. That means any capacitors in series have the same Q. But capacitors in series then get only some parts of the voltage. That means they don't get the entire battery voltage, they get, some share. So now, in terms of if I want to compare V1 and V2, see, here's what I have. Remember that equation that we used? Q over V equals C. See, if I rearrange this, that means solving for V, this becomes Q over C. So that means V1 equals Q1 over C1, V2 equals, Then V2 equals Q2 over C2, all right? So let's say if I want to compare. Well, think like this. So because capacitors are in series, we said that Q1 equals Q2. That means both of them have the same numerator. That means Q1 and Q2 are the same, so I can put as Q. Well, if C1 is equals to C2, then I can put like a C1 over C2. Well, if they're equal to one another and the Qs are the same, so you can see, right, then V1 is equals to V2. Because same Q, same C, you're going to get same voltage. So that's why if capacitors have the same, capacitance, they get, exactly same share of voltage. Well, what if the one of them are not the same? So let's say, for example, C1 is greater than C2. Okay, so let's say this one is 10 microfarad, this one is 5 microfarad. Is V1 equals V2 in this case? Well, of course not, because what I have here is this. Same equation if we look at, right? See, Q1 over, V1 is equals to Q1 over C1. And V2 equals Q2 over C2. They still have the same Q because they are connected in series. But if you divide by C1, this one divided by C2, and C1 is not equals to C2, you're going to get different values for V1 and V2. Now, which one gets more voltage? Well, look at the equation. What does it tell you? Which one will get more voltage? V1 or V2? Considering that C1 is greater than C2. Well, remember, you're dividing by the capacitance. So bigger capacitance gives you smaller voltage. Smaller capacitance gives you bigger voltage. So then technically this is what you will have. The one that is a smaller capacitance gets bigger voltage, which is kind of counterintuitive, but that's what we get. So be careful with that. All right, so then one of the things we can do here is then this. These two capacitors together can be combined into this theoretical one capacitor. That means, for example, right, you have this C1 and you have this C2. Okay, so then theoretically, those two together is what we call equivalent to just one capacitor. Like you can combine them into like one capacitor. But now this C equivalent has then Q divided by V, where V here is the total voltage, right? Or you can say the battery voltage. Remember, total is the battery. Okay. Because why? Because see, this plate is connected to the positive terminal of the battery, this one to the negative. That means voltage of the equivalent capacitance. That means, that means what the battery can see here is the kind of like the overall equivalence of those two together. All right, so then what is the C equivalent? Well, think like this. Remember the condition one, Q1 equals Q2 equals Q. Condition two, V total, okay, is equals to V total, basically the voltage of the equivalent one. So V total equals V1 plus V2, right? Well, we can use this equation to figure out how to calculate, equivalence capacitance. That means what is the effect of having those two in series? Well, using the same equation where C is equals to Q over V and V is equals to Q over C, right? Kind of rearranging that. And coming back to equation 2, then I can write V total as, well, instead of V total, I'm writing Q total over C total, which is basically, for me, total is equivalent, right? Kind of like that. So that means this V represented with this ratio. And this equals to V1 becomes Q1 over C1 plus V2 becomes Q2 over C2. But now I go and look at the condition one, which says Q1 is same as Q2 is same as Q total. They're all the same because Q is constant for the capacitors in series. So I can cancel those. And what I end up with this 1 over C total equals 1 over C1 plus 1 over C2. I end up with basically this equation. Okay. Now, what does it do then to our capacitance? Okay. So what I'm going to do, I'm going to simplify something a little bit and then give you some values. For example, let's take C1 equals 10, C2 equals 10. All right. That means both of them are 10. Now we put them in series together. What is the end result? Well, 1 over C equivalent equals 1 over C1 plus 1 over C2. Let's do this. I want to calculate C equivalent. That means what is the equivalent capacitance? Well, the easiest way is to take both sides inverse of that. So you take inverse of that. So left side, 1 over C equivalent becomes C equivalent. The right side, then what I can do here is this. So 1 over 10 plus 1 over 10 to the negative 1. What I get out of that is this. So it becomes 2 out of 10, right? 2 out of 10 gives me 1 over 5 to the negative 1. Then C equivalent, what is the inverse of 1 over 5? Well, it's 5. And see what happens there. I have 2 10s. I put them together in series, I get 5. I get half of what each one is even. That's because when you put things in two capacitors in series, you decrease the capacitance. And the equivalent you can see is only 5. That means as far as the battery is concerned, there's only 5 farad of capacitance. That's it. You put 2 10s together, but you only get 5 if you connect them in series. So that's kind of like the very counterintuitive, but that's what we get. So when several capacitors are connected in series, the magnitude of charge is the same on all plates of all capacitors. Remember, this was condition 1. The potential difference of the individual capacitors adds to give the total potential difference across the series combination. V total equals V1 plus V2, V3 means that condition 2, which means that voltage is distributed to your circuit element. It means distributed to your capacitors. Then the equivalent capacitance of the series combination is given with this equation. 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 plus that. Means you can have 4, 5, 10, 100 capacitors in series. What happens? More capacitors you put in series, smaller the equivalent. Okay. That means what we have here is this. Remember, this condition 1, condition 2, and this is the end result. Okay. So you are decreasing the capacitance. I'll give you one shortcut equation. See, if you have 1 C equivalent equals 1 over C1 plus 1 over C2. See, if I take the inverse of both sides, the left side becomes just C equivalent. The right side, see inside the parentheses, if I work with 1 over C1 plus 1 over C2, I end up with this. So it's C1, C2 over C1 plus C2 inside the parentheses. You can do the algebra yourself to the negative 1. And if I take the inverse of that, I get this C1, C2 over C1 plus C2. That means this is a shortcut equation that works with 2 capacitors. If you have 2 capacitors, then instead of using this equation, you can use that. C equivalent equals C1 times C2 over C1 plus C2. Remember, we had 2 10s. Let's verify that with this equation. So it becomes 10 times 10 over 10 plus 10. So let's see what we get. 10 times 10 is 100. 10 plus 10 is 20. What do we get? 5, just like before. All right, so you can use this equation. You can use the general equation, up to you. All right, so let's continue and look at a parallel configuration. So what do we get when we connect things in parallel? Well, this is kind of like, let's say, thing like this. So you have capacitor 1, you put capacitor 2, but this time you connect them with 2 wires each side. Here's one side connected, and here's another side connected. That means they are connected on both sides. So this is known as parallel. Remember, the series was this, right? So they only connected in one. So this is series, and that's the parallel. Okay. So now, with parallel configuration, then you can say all those wires those are conductors. So that means they're all electrically connected. That means the left side's electrically connected and the right side electrically connected. So that means here's capacitor 1, capacitor 2. See, their top sides are electrically connected and bottom sides are electrically connected. Now, what we do here is this. See, if I take a battery and I connect it to, let's say, I connect it to this point A and connect this one to this point B. Okay. Well, this point A and point B is technically, connected to the left of C2 and left of C1. B is connected to the right of C2, and right of C1 and connected to the negative plate. That means they're all connected like that. And remember, since the left sides, I'm using this right on the picture on the right. If the left sides are connected to the positive terminal, they're going to be positively charged. The right sides are connected to the negative terminal, they're going to be negatively charged as capacitor is concerned. Also, what I get here is this. Look at the electric field. Electric field going to come like this, hit this point A, and then what? It's a branch. It has two branches, right? It's what we call a junction point. Junction point. Now electric field can go here. So this is electric field 2, and this one electric field 1. That means what you get here, each capacitor gets different electric fields. And the electric field magnitude can also be the same, different depending on the path. That means what we get here is this. Point A and point B represent what we call, again, those junction points. And the electric field, for capacitor 1 and capacitor 2 might be different if they have the different values. But one thing we have is this. See, capacitor 1 and capacitor 2 connected both to that point A and B. See, capacitor 1 connected both sides to A and B. Capacitor 2 connected both sides to A and B. Well, also the battery connected to A and B. That means condition 1 is this. Voltage of capacitor 1 is the voltage of VAB. Voltage of capacitor 2 is also actually VAB, right? It's connected to point A and B. Well, so is, let's say, the total voltage. That means any two capacitors, any 10 capacitors, if they're connected parallel, they all have the same potential. Because see, for example, here's one. Here's the second one. See, they are connected to the same point A and B, right? Well, if I put like few more, see, again, A on one side, B on other side, A on one side, B on other side. See, they're all electrically connected here, all electrically connected there. That means potential difference of any capacitors in parallel, it's exactly the same. But condition 2 tells me that, well, because E1 and E2 could be different, and let's say this, see, E1 is not the same as E total. So E1 plus E2 is E total, right, in terms of electric field, because it splits into two, which means that Q1 that E1 moves and Q2 that E2 moves are, can be also different. And that's not equal to how much E net, E total will be moving. That means the Q total is sum of Q1 plus Q2. That means charges of Q1 and Q2 combined together gives you Q total. So that's the condition for the parallel configuration. All right, so let's see what we get out of that. So this is equivalent capacitor of, two capacitors in parallel. Again, we can just combine them into just one capacitor like that. Okay, what we get here is this. Q total is Q1 plus Q2. Remember that condition. That means two conditions. Condition 1, V1 equals V2 equals V total. Voltage is the same. Condition 2, then Q total equals Q1 plus Q2. Remember the equation, right? Q over V equals C. Then what is Q? Is C times V. Moving the V to the other side. So I'm going to come back to equation 2 and rewrite this by saying Q total is nothing but V total times C total, right? Because if it's Q total and a Q is product of C times V, Q totals only can be in terms of V total times C total. Well, Q1 is C1 times V1. Q2 here is C2 times V2. Well, but condition 1 tells me that all the V's are the same. So then I can come back and I can get rid of the V total, V1 and V2. All right, so what am I left with? I'm left with that C total is nothing but algebraic sum of C1 and C2. That means if I come back to this, to this, let's say, picture here, and I say that this is 10, and this is 10, that means one is 10, the other one 10, then if when I combine them into equivalent, well, this is nothing but 10 plus 10 or 20 farad, let's say, for example, right? That means what I have here is I have algebraic sum of two capacitor values. That means this guy here increases C, all right? If you put two capacitors in parallel, you are increasing the capacitance. You're just adding them together, where in series, you're decreasing the capacitance. So that's kind of like summarize. So when several capacitors are connected in parallel, the potential difference are the same for all capacitors. Condition one. The charges on individual capacitors add to give you the total charge on the parallel combination. Condition two, as we talked about. Then, which means Q total equals Q1 plus Q2 plus Q3, which means the equivalent capacitance is given with this equation. Just C equivalent is C1 plus C2 plus C3 and so on and so forth. That means you are increasing the capacitance, right? You are increasing the capacitance in this configuration. Remember, those are important to understand which one does what, right? Parallel compared to the series. All right. Now, then also how much energy is stored in each capacitor? Well, equation of the energy has three sort of like, let's say three, you can see, right? 1, 2, 3 different formats, but that's because we have three quantities, Q, V, and C that are important for the capacitor. So one equation is then Q squared over 2C. This equation tells you that take the charges, square them, divided by 2 times the capacitance. Well, remember that equation Q, for example, right? Q is equals to C times V. Well, if I take this Q and replace it with C times V, it becomes CV squared divided by 2C. Well, becomes C squared V divided by 2C. Well, I can cancel this with that. Becomes 1/2 C times V. All right, so square, which gives you this equation. That means this is nothing but the same equation, but in terms of using the Q and C, I'm using V and C. How about the other one? Well, you take U equals Q squared over 2C, but remember Q over V equals C. So I say then Q squared over 2 times Q over V. This Q cancels with that, becomes Q, since this is 1 over V, becomes QV over 2, which is that one over there. It's just same thing written 2 different ways, because this one has Q and V, but not C. This one has C and V, but not Q. This one has Q and C, but not V, so like, let's say that. All right, so let's solve some problems. Because then what we're going to do here is we're going to be working with a lot of combination. Let's say capacitors in series, capacitors in parallel, or maybe some that have combination of both together. So here we have 3 microfarad capacitor and 6 microfarad capacitor are discharged and then connected in series. And the series combination is then connected in parallel with 8 microfarad capacitor. Diagram this combination. What is the equivalent capacitance of this combination? All right, so first it was us to diagram this and then find the equivalent. So let's see what we have. So we're given 3 microfarad and 6 microfarad discharged and then connected in series. That means those two in series. So I can write this, okay, so here's 3 microfarad and then 6 microfarad in series. Those are, how do you connect them in series? Then it says the combination is then connected in parallel with 8 microfarad capacitor. That means these are, if I then take the 8 microfarad here, connect this combination connected in parallel with that. That means these are, let's say, wires connected to battery or something like that, right? But this is how you connect 2 capacitors on top in series. Then you connect that combination with the 8 microfarad, parallel to that. So how about the equivalence? So what do we do? So we simplify this. So we take first something that we can easily calculate, which is, the top. That means I can combine them. Remember, I can combine them. So let me go like point A and B like this. So let's say here's point A. So I can combine the top into equivalent like this. and then still have 8 microfarad here. Okay. All right, so what is the equivalent of 3 and 6 in series? Well, remember the equation, right? C equivalent. Remember the shortcut? If you have 2, you can say C1 over C2, C1 times C2 over C1 plus C2. Let's do that. So 3 microfarad times 6 microfarad divided by 3 microfarad plus 6 microfarad. Well, what I get on top here is 3 times 6 is then 18 microfarad squared. Then divided by, at the bottom, I get then 9 microfarad. All right, so this cancels with that. 18 over 9 is then 2 microfarad. That means this is nothing but 2 microfarad. Remember, it's always less than, individual ones, right? So technically, this is 3, this is 6. Connect them in series, you're going to get something that is less than even the smallest one. Okay. Okay, so how about this, this configuration? Well, we have 2 and 8 in parallel. Remember, now, in a way, you can say that this is, let's say, C series, and then this is C parallel. Well, in the parallel, what you get here is then you add them together. So that means you have C1, or like, let's say, if this was C3, right? C3 plus C series then. Well, then I have 8 microfarad, plus now what I got 2 microfarad. Well, I get then 10 microfarad as total. That means having those 3 together is same as having 10 microfarad between those 2 points A and B. The battery sees just that, because between this A and B, all of those 3 together, right, is just equivalent to just 10 microfarad. Technically, then I can just say, all right, so then it's same as not having any of those, but having just 10 microfarad, because those 3 together, right, in that configuration is equivalent to this. All right, so here's one more. And what I'm going to do here is I'm going to draw this for you guys first. And then we're going to do this. And it might look complicated, but let's see what we have. So here's point A. And then we get this. All right, so we start with here. I'm going to put just numbers. So let's say this one is 4 farad, like just 4 in terms of, right? And then we get this. All right, so here's then I have 1 connected with 3. All right, so kind of go like this. Let's look at the bottom. So here we have this. This is 6 connected to, and then this is here then connected to 8, and this one goes here, and this is point B. All right, so seems like really complicated. We have like number of different things, but you will see that it's very easy to actually do something like that if you understand, let's say, the basics of series in parallel configuration. All right, so let's see what we have. So you choose top or bottom first. So let's look at the top first. That means what I'm going to do here, I'm going to let's say, look at just this one. I'm going to make all of them equivalent to just 1. So these are technically known as a simple circle, because I can combine everything that you see in front of you, right, into just one single capacitor. All right, so let's do this. So let's say here's A, right? So if you go above, and then I have this. At the top, I have this, and I have 4, right? So you can see, right? So basically, I have 4 here connected to this guy over here. So let's say what we have. Well, it's 1 and 3 in parallel. So remember, what is 1 and 3 in parallel? Well, 1 and 3 in parallel, equivalent, I can just write like this, equivalent. And equivalent capacitance, remember, because they're parallel, is just a sum. So 1 plus 3 is equals to 4. That means that configuration is just this. Okay, that means top now simplifies into that. All right, so how can I simplify even further? Well, I can combine those 2 together. Well, what do I have those 2 together equivalent to? Well, I can say, okay, so this is A, goes to the top, and those 2 become just 1 to get to B, right? And this is 4 and 4. Now, you can use this equation, right? So C equivalent is equals to C1 times C2 over C1 plus C2, which is 4 times 4 over 4 plus 4. This gives you 16 over 4. or sorry, 16 over 8, and that's 2. That means this is 2. And let me give you like a, one thing that you can always, work with. See, this is 4, this is 4. That means they're identical. 2 identical capacitors in series. What will be their equivalent? Half. How about if this was, let's say, 10 and 10? What would have been equivalent? Well, half would have been 5. 100, 100, this would have been, let's say, 50. That means this is something that to remember. If you have this is 4 and this is 4, their equivalent always half. So this is 2. That means going from A to B, all of that at the top is just like one capacitor with 2. Now let's look at the bottom and simplify this. So here we have this configuration first, and this is 6 and 2 in parallel. What is the equivalent? Well, remember, it's sum. 6 plus 2, well, it's 8. And it's connected to this guy in series, which is another 8. Then this is A to B. Well, then what will be equivalent for those two? That means how can I combine those two series, 8 farad, right, or whatever configuration? Well, again, identical, right? 8, 8, equivalent is half, so it's 4. That means going from there to here, we have this. At the top, we have 2. At the bottom, we have 4. That means we have this. So let's say here's A, goes like this, which is 2 over there, and goes like that, and this is 4 over here. And this is then point B. Then what is the equivalent of this final, let's say, or pre-final configuration? Well, you have 2 in parallel, 2 and 4. What is the equivalent? Well, it's algebraic sum, right? That means this is 2 plus 4, which is 6. And that's the answer. So you can see, right, it's pretty straightforward once you kind of understand how to work with those, how to add them together and things like that. All right. So one more example here. So this is a little more complicated one. So you have to kind of, pay attention to everything that we're doing here. So you have 10 microfarad capacitor and the 20 microfarad capacitor are connected in parallel across the terminals of 6-volt battery. Okay. Let's see what we have. The 10 and 20 are connected in parallel. So let's call this 10, C1. Connected to parallel to each other. So then C2 is equal to then 20 microfarad. And they're connected to the battery. And here's then the battery. Hopefully you guys are able to follow the circuit diagrams. Positive, negative. All right, so then we're given that the battery voltage is 6 volts. So 6 volts, VV. Basically V total, right? Same as V total. Okay, so this is my configuration. Sometimes I put like this is point A to point B to make it a little bit easy. It says, what is the equivalent capacitance of this combination? Okay, so let's look at A. Well, equivalent is this, right? C equivalent, and since this is in parallel, so this is C1 plus C2. That means it's easy, right? 10 microfarad plus 20 microfarad gives you 30 microfarad. That part is easy. Part B, what is the potential difference across each capacitor? That means we're asking what is the potential difference across this one, which is V1, and across that one, which is V2. All right, so let's look at it. So that means you want to know that potential difference between, capacitor 1, right? So that means see capacitor connected on the left side to point A, on the right side to point B. That means V1 is equals to VAB. But VAB, right, point A is connected to then positive and negative of the terminal. That means V1 has the same as VB is 6 volts. How about V2? Well, V2 is also connected to points V and B. That means V2 is equals to the point VAB. Well, VAB is the same as, like, let's say the battery, right? That means it also have 6 volts, which should make sense, right? Because these are parallel. V1 equals V2 equals V total, right? Let's say that V total is directly connected to the battery. That means at least this is going to be always true. And if this configuration connected to the battery directly, then it's equals to the V total. Or you can say like this, it's equals to VP. parallel configuration. Part C, it says find the charge on each capacitor. Remember, that means I want to know Q1 and I want to know Q2. Well, remember, how do I find Q1? Well, using the general equation, Q1 is equals to C1 times V1. Remember that general equation, right? Q over V equals C. We use this a lot. I rearrange Q equals C times V. So Q1 equals C1 times V1. And luckily we have that. So this is 10 microfarad for C1. V1, we just got that it's 6 volts. So I can calculate this to be 60 microcoulomb. Q2 is C2 times V2, which is now 20 microfarad times 6 volts. What do I get? Well, you can see, right, because C2 is double, the Q2 is double, and it's actually 120 microcoulomb. So that's why Q1 and Q2 are not the same, right? So the total will be then the sum of it, right? Total Q will be 180 microcoulomb, sorry. Part D then, find the energy stored in each capacitor. That means, you know, A, B, C, D here. Remember, the energy stored is U is equal to, and I have 3 versions of that, right? So you can use either one of them. So usually I use this Q times V because simply I don't have to square anything. So let's say U1 equals Q1 V1. That means it's 1/2 60 microcoulomb times 6 volts. This should give me 180 microjoules. U2 then is equals to 1/2 Q2 times V2, then 1/2 120 microcoulomb times 6 volts. And this gives me 360 microjoules. Right, so something like that, right? All right, so that's why you have to kind of be careful and look at each one sort of individually. But this is like the idea for something like that. All right. Now we're down to sort of like the last thing we have in this chapter, which is looking at what we call capacitors with, instead of vacuum between the plates, we put there some kind of insulator between the plates. So we call it a dielectric. So you can see, right, most capacitors have non-conducting material or dielectric between their conducting plates. And the most common you can see, right, are the metal foil, you know, let's say for the plates separated with strips by sheet of like mylar or something like that. That means, you know, metal foils are the conductors, so the plates, and you put them some kind of, you know, plastic or something like that, right, mylar. So what is the purpose of doing that? We're going to see that you can use it to actually increase the capacitance without changing the geometry of the capacitor itself. So for example, so let's say we have this capacitor with vacuum between the plates. And look at, we're measuring then, you know, the potential difference using the voltmeter. Look at the reading. Look at the reading. This is being 0. So this is the voltage between the plates if you have a vacuum. Okay, so let's call this C0, which is the capacitance now, is Q0 over V0 using that equation. 0 means initial. Okay. Now what we do then is we then put some kind of dielectric, you can see, right? Put some kind of dielectric like a glass, paraffin, polyester, and things like that. But if I do that, I'm not changing capacitor plates at all, in no way. I'm not changing same plates. What I get here is this. The Q is unchanged because I have the same area, right? So only when I change the area, you know, it will change. But here's, look at the voltmeter reading. Remember, it was here before. Now it's over there. That means V final is less than V initial. That means, you know, V final now is less than V before. Well, it means then my Q initial and final are the same. So let's say Q final is equals to Q initial, but my voltage before and after changes. See, if I then do this, right? C final, which is equals to Q final over V final, because the Q final is same as Q initial before, but C final will be different because V final is less than before. Remember, so right now, if I put V final, final voltage, and this is a smaller number, because let's say this is a smaller number, C final will be a bigger number. Okay, that means C final, final capacitance that I get, is going to be greater than initial capacitance I had before. That means the advantage here is this: without changing the geometry of the capacitor, I'm increasing the capacitance by some factor only because I put that capacitor, the dielectric inside. What it does, it makes it voltage decrease, and in that, in that case, I'm getting the capacitance increase. The reason is because when I have a vacuum between the plates, look at the electric fields. Those are uniform electric fields from positive to negative plates. I put the dielectric here. What it does here is then it creates sort of polarity inside. And that polarity, so let's say, decreases the amount of electric field I have. Kind of like cancel some of the electric field. And remember, the V is E times D, right? D being the distance between the plates. Well, if I'm decreasing the electric field, keeping the distance constant, I'm decreasing the voltage. That means due to this polarization of the charge within the dielectric, you get basically smaller voltage. You're decreasing the potential, right? You're decreasing electric potential because you decreasing electric field. Which means that putting this insulating, a material between the plates, you are able to increase the capacitance, and sometimes by a really large factor. So we use this factor K to represent it as a dielectric constant, and you can say then this final capacitance is equal to some factor K times the initial capacitance. So this K is known as a dielectric constant. So K here, remember the initial capacitance, basically is, using the geometry, is the area times epsilon naught over D, right? That means I can have this equation now for the capacitor. That means now capacitor is equals to K times epsilon naught A over D. That means this is kind of like the modified equation. And K is equals to 1, so if basically you had vacuum. So if you have vacuum, K equals 1, so you're down to the same equation as before, right? So you get this. That means K is equals to 1 for vacuum, and then greater than 1 for anything else. So that's why you can only increase the capacitance by using the dielectrics. And for example, here I have some a table with some of the values. So you can see, right, vacuum is 1. So if you have air, you can technically treat it as vacuum as well, because up to several sig figs is still 1. So you put Teflon, it's 2.1. That means it's double the capacitance. Mylar triples the capacitance. Look at this, water makes the capacitance 80 times bigger. That means if you put the capacitor and fill the distance between them, that area, with water, you increasing the capacitance by 80 times. All right, so let's then look at this example and see how we can use all that to calculate a problem. So you're a material science engineer and your group has fabricated a new dielectric that has an exceptionally large dielectric constant of 24. Not as large as, let's say, water, but still relatively large. Now, then what we have here is this. The electric field is 4 times 10 to the 7 volts per meter for the dielectric. And suppose you want to use this material to construct a 0.1 microfarad parallel plate capacitor that can withstand a potential difference of 2000 volts or 2 kilovolts. What is the minimum plate separation required to do this? And what is the area of each plate in this separation? Okay, that means what we want to find is the D, right? So technically, let's say what we're given here is K. K is 24. Remember, it has no units, just 24. We're given electric field, 4 times 10 to the 7 volts per meter. We're given the capacitance, 0.1 microfarad. We're given that voltage that we want here is 2000 volts. So that's given to us. Then what we want to find is D, distance between the plates, and area of the plates. All right, so remember, to do that, we technically have one equation, right? C equals K epsilon naught A over D. But in this particular equation, for now, I have, let's say, two unknowns. I don't know area, I don't know D. I can't use this equation, even though I have C, K, and epsilon naught, but I don't know A and D. So in one equation, two unknowns, I'm stuck. All right, so what we do here is we try to find at least one of them different way. And I can do that because I have electric field and I have voltage. And I know that if I have, let's say, plates that are separated by distance D, there's an electric field between them that's also related to the V, let's say delta V of the, of those parallel plates. With this equation, remember, delta V over D is equals to E, or D is equals to then delta V over E. So I can use these two equations to find D, which is then 2000 volts over 4 times 10 to the 7 volts per meters, to find that the distance here is 50 times 10 to the negative 6 meters, or 50 micrometer. All right, now that we found one of them, it's then easy to go and get then the other one, right? Because now I can use this equation to say then area is equals to C times D over K times epsilon naught, and you solve for that. C is 0.1 times 10 to the negative 6 farad. D here is 50 times 10 to the negative 6 meters, divided dielectric constant of 24, then epsilon naught, which is 8.85 times 10 to the negative 12. Remember, so it's Coulomb square over newtons times meter square. That's the units for that. I remember I might have got the units wrong like last time. So Coulomb square over newtons times meter square. We do that, then we're gonna get area as 2.35 times 10 to the negative 2 square meters, or 240 centimeters square. And that's the area of the plates that needed to withstand 2000 volts of voltage. All right, so this concludes then chapter 18.